Today we're covering material from section 4.2, all about graphing polynomial functions. Here are our objectives today. It includes graphing the polynomial functions and the intermediate value theorem. So if p of x is a polynomial of degree n, then the function has at most n zeros, and hence at most n x-intercepts. It also has at most n-1 turning points. And a turning point on a graph is where we see the relative mins or maxes occur, essentially where we change from increasing to decreasing or decreasing to increasing. So if I have a polynomial, let's say like x to the 7 plus 6x to the 5 plus 1, I know my n is 7, so we can have at most 7 zeros and 6 turning points. n-1 here is 6. Okay, so that's kind of the concept. So looking at our graph, x cubed minus x squared plus 8. Our degree, our largest exponent essentially here is 3. So the maximum number of zeros we can have is 3. And the maximum number of turning points is 3 minus 1, which is 2. Now for the second part, the degree is 9. The maximum number of zeros is then, again, 9. And the maximum number of turning points is 9 minus 1, which is 8. Again, it all is based off of that leading term. Please note that if this were written something like negative 9x squared plus x to the 9 plus 7x, minus 8, you still need to pick up that x to the 9 is still the largest term. So they're not always written in standard form. You have to get used to making sure that they are. These examples just happen to be. Now we want to get used to actually graphing the polynomial functions themselves. So we're going to go through this 6-step process, and we're going to do 2 examples so you can see how it's done. The first step is to always look at the end behavior. Now, we covered this in lecture 4.1, where we talked about using the leading term to figure out what the graph does at its ends. So what happens on the left side of the graph and the far right side of the graph. This is where we're thinking about, is my leading coefficient positive or negative, and is my degree even or odd? Then we're going to look at the zeros and their multiplicities. Remember that this is where we cross the x-axis, or maybe where we just touch the x-axis. Then we're going to talk about determining the sign of each interval to help us figure out if we just cross the axis or not, and kind of what direction and how far we're going. We're also going to find the y-intercept, so plug in x equals 0 if that wasn't one of our zeros already. We'll plot a few more points if we need to, and then we'll draw a smooth curve. So let's see this in action. Here we have negative 2x to the 4th plus 3x squared. So with this end behavior, we know we're looking at something that is negative, and we know it's even. So we know that our shape is going to kind of do this, right? We know it's negative, so we know it's pointing downwards on both sides, and it's even, so we know it's the same thing on both sides. Now to find the zeros and multiplicities, we of course need to factor this. So they each have an x cubed term in common. That leaves me with a minus 2x plus 3. Now if I have these two things, I need to set each thing equal to 0. Typically we leave out the exponent though, so we get x equals 0 and negative 2x plus 3 equals 0. Here if I subtract 3 on both sides, I get negative 2x equals negative 3. And so I get x equals 3 over 2. So x equals 0 has multiplicity 3, right? That came from our x cubed term. And then our x equals 3 halves has multiplicity 1. So that's going to help us know that both of these are actually going to cross the axis. Remember when our multiplicity for each 0, here being x equals 0 and x equals 3 halves, they both have odd multiplicities, so we know they're both crossing the axis. So determine the signs of the surrounding zeros. This is where we want to kind of think about what's happening along our axis. So if I know that these are the two places where I cross the axis, I want to know, did I go from positive to negative, so cross it like that kind of motion? Or did I go from negative to positive, so I crossed kind of like that? Well, let's find out. I'm going to pick a test point, something like -1 and 1, and see if I went upwards over the axis or if I went downwards over the axis, okay? So to plug these into the actual function, if I plug in -1, then I have -2 minus 3, which is -5. So I know I'm starting off negative here. If I plug in 1, I'm looking at 2 times 1 plus 3, so 1 comma 1, right? That's the other point on this function. Again, you're just plugging in, like, what is h of -1? That gave us -5. Hello. And then h of 1 gave us 1. And let's do one more test point out here of 2. And we know we're having the point then 2 comma 2 to the 4 is 16 times 2 is -32 plus 24 is -8. I think that sounds correct. So we know we're going negative plus negative. Essentially, I know I'm crossing the axis in a downward motion here and an upwards motion here. Right here. That was the important part of this little part. This will make more sense once I start actually putting it on the graph. You'll see what happened. But again, I just start with my zeros in here, and then I'm picking these test points. So I know -1, -5, 1, 1, and 2, -8 are all on my graph. That'll count as plotting some points here, and it's usually helpful to also kind of help us determine the signs. We also don't have to worry about the y-intercept step here because one of our zeros was x equals 0. So as soon as I plug in x equals 0, I get the point 0, 0. That was already covered here in this example. So now we just got to actually draw it. So here it is on the next slide. You can see that I wrote down notes ahead of time. We have our even, negative, overall kind of look to the function. We know we have 3/2 comma 0, multiplicity 1. We have 0, 0 with multiplicity 3. And then we have our different points that we marked on the graph and on our number line. And of course, then we marked that this went minus, plus, minus. So let's put some of these down. I know I'm going to use the even negative part in the end, but I know I'm going to go through the point 0, 0 and 3/2 comma 0. I also know I have the point -1, -5, so -1, -5. I have the point 1, 1, which is up here, and I have the point 2, -8, which is down here. And knowing my even negative kind of is helpful now because I know that it's having this kind of shape overall. So as soon as I start to connect my points, I know it starts to look something like this. And I can draw my arrows, and maybe it kept going up here and then came back down. I don't really care. I know it goes through that point and just keeps coming back down. You can throw it in your calculator if you want to be more precise. But this is what we know at this step with this information. So this is the sketch we're going to go with. Just to check our work, notice we are doing the down, down of even negative. We are crossing the axis at our odd multiplicity x-intercepts. And we do actually go from below the axis to above the axis to below the axis. So all of that looks correct. Now let's look at a different example. And this one's already factored for us, which is nice. To talk about its end behavior, notice that we're negative overall, and we have a odd function overall. To find the zeros and multiplicities, we want to take x minus 2 and set it equal to 0. We get x equals 2. Now determine the signs surrounding the zeros. I take out my number line and I throw a 2 on there. Let's see what's happening at 1 and at 3. At 1, if I plug it in, if I plug 1 in here, I'm looking at 1 minus 2 cubed. That's -1 cubed, which is -1. With the negative out front, that's a +1. And if I plug in 3, I get -1 as the output. So there I have my 2 points I know are on the function as well. Okay, so I know the overall trend goes plus minus. That tracks with my multiplicity being odd. I guess I didn't write that down. Our multiplicity here is 3. So we are actually crossing the axis from plus to minus. Perfect. Now to find the y-intercept, I want to plug in x equals 0, and I get -2 cubed, which is 8, positive 8. So this is the point 0, 8. That's also helpful. Our plot the points is really covered by our number line work, and then we're going to draw our curve. So going to the next slide, again, I kind of wrote down some of these things already. So we have that it's negative and we know it's odd, which we know is going to be like this shape. Our x-intercept is 2, 0 with multiplicity 3, and we had our little number line written out and our y-intercept. So to plot some of these things, I plot 2, 0. I'm going to plot 1, 1. Let's plot 3, -1. And we're going to plot 0, 8. And we're going to remember that over here we have our overall trend that we're looking for. You can kind of see it coming out of this shape. So I know it's going to come down like this and swoop. Oh no, I lost it. Come down like this and swoop through right at our x-axis here, and then start going down kind of like this and keep going. And I draw my little arrows, and notice it is that shape that we're expecting. It has the multiplicity 3. It actually has it crossing the axis. We're going through our points, and we hit our y-intercept. So this is a pretty good drawing of this graph, and it's pretty close to the original if you pull it up in your calculator. Now we have one quick theorem to kind of wrap up this lecture. Here we have the intermediate value theorem, and to put it in plain English, it says if you plug in two x values, you get a positive output for one and a negative output for the other, then the graph must have crossed the x-axis somewhere in between. So that means there is a 0 between these two values, right? If I have a graph, and let's say I have a point down here and a point up here, then of course my graph crosses the axis at some point. Formally, if I were to write this down, we would say if P of A and P of B have opposite signs for some polynomial P of X, then P has at least one real 0 between A and B. But sometimes the picture and the just kind of natural language is a little bit more easy to understand. What we need to note, though, is if our outputs P of A and P of B have the same sign, the theorem tells us nothing. We cannot say there are no zeros there because we just can't tell. We don't know if our function actually looks something like this, that goes up here, drips below the axis, and comes back up. If all we see are these 2 points, we don't know if there's a 0 or not. We don't know if we drop below the axis or if we drop something like this. Can't tell. So we say that the theorem's inconclusive here. So for an example, if we're looking at f of x equals x cubed plus x squared minus 6x, and we're given our a value of -4 and b of -2, well, if I plug in -4, I get -4 cubed plus -4 squared minus 6 times -4, and I get -24. Then if I look at f of -2, I'm looking at -2 cubed plus -2 squared minus 6 times -2. And if I put all that in my calculator, I get 8. So that means if I'm looking at my graph, something like this, and let's say here's 4 and here's -2, I know -4 goes down here to somewhere to -24. Let's just call it there. And I know -2 is sitting somewhere up here. Let's call it 8. So I know my function's doing something like this. And yes, I am in fact crossing the x-axis. So yes, I do have a 0. Essentially because my y value is -24, my for the first one, my y value is then 8 for the second one. I know I must have crossed the axis at some point to go from negative 24 to 8. So yes, there is a 0 between negative 4 and negative 2. Now let's test the other one. Now if I look at f of negative 1, which is negative 1 cubed plus negative 1 squared minus 6 times negative 1, which gives us 6. And I look at f of 3. I have 3 cubed plus 3 squared minus 6 times 3, and that is 18. Now these are both positive. Well, that's a problem. I can't tell if we cross the axis or not, so we say we cannot tell. We don't try to say a conclusion about that maybe it crossed the axis or not. We have no idea. So we say we cannot tell. We call it a day. And that is it actually for this lecture. So as always, please reach out if you have any questions.